Hello, this is our CS225 final project presentation where we are just going to go over some of the work we did and see how it's all working. So we'll be on the way then.
So our goals for this project were to find these strongly connected components of a graph, and then given to any two specific web pages, find the exact list of pages that are shortest path between the two pages, and then find the top 10 web pages on a based off the PageRank algorithm. So what we accomplished was that we successfully created a graph class that can ingest graph data. We had the BFS traversal and the shortest path calculation. We calculated connected components, the PageRank algorithm, and we wrote out tests for our codes. We did complete all of the goals that we had for the project, but we could have cleaned up some code, made the project a little bit better, and added some more testing.
Okay, so the very first thing we want to look at is the graph class and the project setup. So when looking at the graph, we decided to use the adjacency list to represent that graph, obviously for some time benefits over the adjacency matrix. And we ingested the graph using a text file where each singular line of the text file was a new node. And then we had space separating the different edges of the node, as you can see represented by the bottom left picture. And then the bottom right picture actually demonstrates how that graph was then ingested. And then using the output operators, we output the nodes that it just took in. And then we used CMake-list to build the project's makefile, download catch2, and just handle all of that dependency and project setup stuff so it works a little more seamlessly.
So for our graph traversal, we chose to do BFS, and this is the preferred traversal for our directed graph because it helps with finding the shortest path easier. So one of the functions that we have for just running BFS given a specific source node runs BFS from that node and just goes out as far as it can. This would just calculate a weakly connected component of the graph. And then the get shortest path method can be run after the BFS of in source method has been run, and it returns a list of nodes from the source to the destination. And then the BFSL function uses the BFS helper function to visit all nodes throughout the entire graph because the graph is disconnected, obviously. So we have to run BFS for every connected component. And then this BFS all returns a vector of all the nodes traversed in that order. And BFS is an O of V plus E algorithm because it has to traverse over every single vertex and every single edge. So if we look at the image in the middle, basically it just shows that the functions are working as desired, and the image on the right prints out all the nodes traversed, and we will show this later in our VS Code demo.
Right. So for the PageRank algorithm, we decided, since we're using such a large data set, decided to use the eigenc++ library. And with this library, we're able to perform linear algebra that is used for the PageRank algorithm. Specifically, the sparse matrices enable us to compute the PageRank algorithm in pretty good time. The PageRank class constructor itself is what created the adjacency matrix, and the adjacency matrix is used to transition, the eigenvector probability distribution and the PageRank class constructor creates also the eigenvector, which is the probability distribution of the number of nodes of the graph itself. So after those were created, the run PageRank algorithm iterates by par method. And this is iterated for a number of times until the eigenvector converges to a stable probability distribution. And this just represents, the probability of someone randomly picking a web page based off the PageRank algorithm.
Okay, and so for our strongly connected components algorithm, we decided to utilize Kosaraju's algorithm. We saw there were a couple different strongly connected component algorithms, but we felt like this one was the most simplistic and accessible for us to use. It has an O of V plus E time complexity, which makes it pretty good, not anything horrible. And what it does is it does two separate DFS traversals. And some of the reason we decided to go with DFS over BFS, which we use for the shortest path, is just after reading some material, DFS seemed like the more easy method to structure the algorithm so everything stays a little more simple. And then the algorithm returns 2D vector containing vectors that each represent a component. And you can see a picture over the right there has a list of some of the different connected components within our example and the number of connected components there at the bottom of the image. And so for looking at the testing of our actual entire project, you can review the test that we wrote for our algorithms if you want to go line by line, section by section, and see all of those assertions. It is all located in our test directory where we separate out the different tests into different files, with the test main file just being there to declare catch and set all of that up. And then our code has passed all of our test cases, local computers, as well as on EWS. So we haven't had issues with any of that. You just need to ensure that you have Catch2 installed, which requires the certain version of CMake for that all to work together.
So in our conclusions, we got that there's 29,916 strongly connected components. We ran the BFS in source and then got get shortest path in S to find the exact list of web pages in the shortest path between 2 pages. And we can print the top 10 pages according to PageRank. We would like to be able to know what actual web page each integer node represents. We gained experience with CMake and collaborating on GitHub. And given more time, we could have implemented even more algorithms, such as displaying our results in a visual way using a force-directed graph.
Okay, and with the very little amount of time we have left, without going too far over, we'd like to quickly show off some of the algorithms actually working for us. So with the very first thing, we can show we're in the build folder as highlighted right there. We can run CMake, and all of this is listed in the README as well. Make to actually build it. And then if we run main quickly, the first thing we have showing is the shortest path, which will show all of this different information about a small little test there. And then going through, it will explain all of this information about going through the shortest path. And then if we want to actually uncomment these lines here, we leave it commented for the usual class just because of the fact that it shows so much. But if we want to run it again with those lines uncommented right there, that's an entire BFS traversal there of the graph. And moving on quickly, I can then show us the algorithm of strongly connected components, which right here, if I can uncomment it. This part right here will run the connected components, and then we can uncomment these two lines right here. And with that, it will then go through and then show the number of connected components as well as the number of components in the graph as a whole. And if we wanted to, I can quickly print out as well the actual connected components by uncommenting another line and then just printing it out. As we see there, all of the different connected components. And then last but not least, we can quickly show the PageRank as well. And what this will do is show all of those different iterations we're going through of calculating those values, as we see. And while that's running as well, I can quickly show the testing suite as well, we just have to run make and then the test command. And then as you see, it's running through all the different tests and it passes 117 assertions in 10 cases. If we go back over, we can see our PageRank is still running through all those iterations. It will go up to 1,000, I believe. And once we get there, we can see that all the different algorithms will have completed. And there we go. And so that is a quick run through of our different stuff. Thank you so much and have a great day.